When we look up at the night sky, we see stars, planets, and faint clouds of light stretching across the darkness. Almost everything we notice is defined by what it emits or reflects. Light becomes our guide. Yet for more than a century, scientists have known that much of the universe does not behave as it should if light were the whole story. Galaxies move in ways that seem calm and orderly, but their motion quietly suggests that something unseen is present, shaping everything from behind the scenes. This unseen presence is not an idea that comes from imagination or philosophy. It comes from careful measurement, from watching stars orbit the centres of galaxies, from tracking how clusters of galaxies hold together across enormous distances. Again and again, the same conclusion appears: there is more matter than we can see. Not just a little more, but much more. Enough to outweigh everything made of atoms, planets, stars, and gas. This is where our question begins, gently and directly. What is dark matter exactly? Welcome to AstraFlow. Here, science drifts like starlight, and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing soften, and your mind settle into quiet understanding. If you're listening from a familiar place, perhaps a bedroom or a quiet room late at night, you're not alone. People from many parts of the world let these questions play softly as they rest. If you feel like it, you're welcome to share where you're listening from in the comments, and if these calm explorations help you unwind, a gentle like or subscription helps this space continue. Now let's begin and explore the science of what dark matter is. Exactly. To start, it helps to ground ourselves in what we already know. Matter in everyday life is easy to recognize. It has weight, it takes up space, it can be touched, heated, shaped, or broken apart. The matter we are familiar with is made of atoms, which combine into molecules, forming everything from air and water to planets and stars. This kind of matter also interacts with light. It can glow, reflect, absorb, or scatter it. Because of this, telescopes can detect it even across vast cosmic distances. Dark matter is different in one very specific way. It does not interact with light in any detectable manner. It does not glow when heated. It does not reflect starlight. It does not block light the way dust clouds do. If light were the only thing we could measure, dark matter would appear to be completely absent. And yet, its presence is revealed through gravity, the quiet force that shapes motion across the universe. Gravity does not care whether something shines, it responds only to mass. When astronomers observe stars moving too quickly to be held together by visible matter alone, gravity points towards something hidden. When clusters of galaxies remain bound instead of drifting apart, gravity again suggests unseen mass. These patterns are consistent, repeated, and measurable. Dark matter enters the story not as a guess, but as the simplest explanation that fits what we observe. As we move forward, we'll take this idea step by step. We'll look at how scientists discovered the problem, how they tested different explanations, and how dark matter fits into the larger structure of the universe. There's no need to rush. These ideas were built slowly, over decades through careful observation and patient reasoning. Tonight, we'll follow that same pace, calm, steady, and grounded in what can be known. When scientists talk about matter, they usually begin with a simple distinction. There is matter we can detect directly, and matter we infer indirectly. The first category includes everything made of atoms. These atoms combine into molecules, and those molecules form stars, planets, gas clouds, dust, and living beings. This kind of matter interacts with light in familiar ways. It can emit light, like stars. It can reflect light, like planets and moons. Or it can absorb light, like interstellar dust. Because of this interaction, telescopes are very good at finding it. Astronomers give this familiar category a name: ordinary matter, sometimes called baryonic matter. Despite how dominant it feels in daily life, ordinary matter makes up only a small fraction of the total mass of the universe. This is not an abstract estimate. It comes from multiple measurements, including the behavior of galaxies, the structure of galaxy clusters, and the subtle patterns left over from the early universe. Each method points to the same conclusion. Most matter does not belong to this familiar category. The second category is what we call dark matter. The word dark here is precise, not dramatic. It simply means that this matter does not interact with light in a detectable way. It does not shine, it does not reflect, it does not absorb. If a large amount of dark matter were placed between us and a distant star, the star would still appear just as bright. Nothing would seem to be in the way. At first, this idea can feel strange. In everyday experience, we rely on light to tell us where things are. But physics does not require matter to interact with light. Light is just one of several fundamental interactions. Gravity is another. And gravity, unlike light, responds to all mass equally, whether that mass is visible or not. This difference explains how dark matter entered scientific thinking. Astronomers did not set out to invent a new type of substance. Instead, they noticed that visible matter could not account for the gravitational effects they were measuring. Stars were moving too fast. Galaxies were rotating in ways that should have caused them to tear themselves apart. Galaxy clusters remained intact when visible mass alone could not hold them together. Something else had to be present. It's important to pause here and be clear about what dark matter is not. It is not simply empty space. Empty space has energy and structure, but it does not behave like mass in the same way. Dark matter adds gravitational pull, it contributes weight, it shapes motion. This means it must be some form of matter, even if it is very different from the kind we know. It is also not a flaw in measurement or a misunderstanding of basic physics, at least not one that has been easily resolved. Over many decades, scientists have tested alternative explanations, recalibrated instruments, and repeated observations using different methods. The discrepancy remains. Wherever we look, from small galaxies to the largest cosmic structures, the same pattern appears. A calm way to think about this distinction is to imagine standing in a dark room with your eyes closed. You cannot see the furniture, but if you walk forward, you will feel resistance. The room is not empty just because it is dark. In a similar way, the universe is not empty simply because much of its matter does not emit light. Gravity allows us to feel its presence, even when sight fails. As we continue, we'll move from this basic distinction toward the specific clues that reveal dark matter in action. The story becomes clearer not through speculation, but through careful observation of how things move, slowly and consistently, across cosmic time. To understand how dark matter reveals itself, we need to slow down and focus on gravity. Gravity is the most familiar of the fundamental forces, yet it is also the most subtle. You feel it as weight. You see it in falling objects. In space, gravity quietly governs the motion of stars, planets, and entire galaxies. Most importantly for our story, gravity responds only to mass. It does not depend on whether that mass shines, reflects light, or remains completely invisible. This makes gravity a powerful tool for discovery. Even when something cannot be seen directly, its mass can still be measured through the way it pulls on other objects. In astronomy, this principle is used constantly. The mass of planets is calculated by watching their moons. The mass of stars is inferred from the motion of companion stars. In each case, movement becomes evidence. When astronomers began measuring the motion of stars inside galaxies, they expected gravity to behave in a straightforward way. Most of a galaxy's visible matter is concentrated near its centre, where stars are dense and bright. Farther out, the number of stars drops off. Based on this distribution, stars near the edges of galaxies should orbit more slowly than stars near the centre, much like planets in our solar system. Mercury moves faster than Earth, and Earth moves faster than Neptune, because most of the Sun's mass is concentrated in one place. But galaxies did not behave this way. As astronomers measured star speeds at increasing distances from galactic centres, they found something unexpected. Instead of slowing down, stars far from the centre were moving just as fast as those much closer in. In some cases, they were moving so fast that the galaxy should not have been able to hold together at all. According to visible matter alone, these stars should have drifted away into intergalactic space long ago. Gravity was clearly present, strong and consistent. The problem was not that gravity was missing. The problem was that there was not enough visible mass to explain how strong gravity appeared to be. Something else had to be adding to the gravitational pull. This realization was not immediate, and it was not dramatic. It emerged slowly as measurements became more precise and were repeated across many different galaxies. The same pattern appeared again and again. Wherever astronomers looked, gravity seemed to be stronger than visible matter allowed. One possibility was that scientists did not understand gravity correctly at large scales. This idea was taken seriously and explored carefully. But any modification to gravity had to explain not just one observation, but many. It had to account for galaxy rotation, galaxy clusters, gravitational lensing, and the structure of the universe as a whole. So far, no alternative explanation has matched all of these observations as consistently as the presence of additional matter. Another possibility was that the missing mass was made of ordinary objects that were simply hard to see, such as faint stars or cold gas. But careful surveys ruled this out. There was not nearly enough hidden ordinary matter to account for the gravitational effects being measured. What remained was the simplest explanation that fit all the data. There is additional mass in galaxies and clusters that does not interact with light. This mass forms a large extended halo around galaxies, reaching far beyond their visible edges. Stars orbit within this invisible structure. Guided by gravity they cannot see. An everyday comparison can help here. Imagine watching leaves swirl in a stream at night. You cannot see the water clearly, but the motion of the leaves tells you how fast the current is flowing and where it is strongest. In the same way, astronomers watch stars and galaxies move, and from their motion, they infer the presence of something unseen. Gravity, in this sense, acts like a quiet translator. It turns invisible mass into visible motion. It does not tell us what dark matter is made of, but it tells us with steady reliability that it is there. As we move forward, we'll look more closely at one of the most important pieces of evidence in this story, how stars move within galaxies and why their speed reveals so much about what cannot be seen. Once gravity became the key clue, astronomers turned their attention to one of the most measurable features of galaxies, how fast their stars move. This may sound abstract, but it is something scientists can observe with great precision. By studying the light from stars, astronomers can measure tiny shifts in wavelength caused by motion, known as the Doppler effect. From these shifts, they can calculate how quickly stars are orbiting the centre of a galaxy. At first, the expectation was simple. In any system held together by gravity, orbital speed depends on how mass is distributed. In our solar system, nearly all the mass is concentrated in the Sun. As a result, planets closer to the Sun move faster, while those farther away move more slowly. This pattern is stable and predictable. Scientists expected galaxies to behave in a similar way, with stars near the centre moving quickly and stars farther out slowing down as the amount of enclosed mass decreased. But when astronomers actually measured these speeds, the results did not match that expectation. In many galaxies, stars far from the centre were moving just as fast as those much closer in. Instead of declining with distance, the orbital speed stayed nearly constant. This pattern became known as a flat rotation curve. The word flat here is descriptive, not emotional. It simply means that speed does not drop off as expected. This observation was surprising because it challenged a very basic relationship between gravity and motion. If only visible matter were present, the outer stars should not be moving so fast. There would not be enough gravitational pull to keep them bound. According to calculations based on visible mass alone, these stars should escape the galaxy entirely. Yet galaxies are not flying apart. They are stable structures that persist for billions of years. Their stars follow smooth, orderly orbits. This stability tells us something important. The gravitational pull holding these galaxies together must be stronger than what visible matter can provide. To explain this, astronomers propose that galaxies are surrounded by large halos of unseen mass. These halos extend far beyond the visible edges of the galaxy, enclosing it in a much larger gravitational structure. Within this halo, stars orbit under the combined influence of both visible matter and this additional invisible mass. It's worth noting how carefully this conclusion was reached. Scientists did not observe one unusual galaxy and generalize from it. They measured hundreds, then thousands of galaxies, spiral galaxies, elliptical galaxies, large ones, small ones, nearby ones, distant ones. The same pattern appeared again and again. Flat rotation curves were not rare anomalies. They were the rule. Over time, measurements became more accurate. Instruments improved. Data sets grew larger. Still, the results remained consistent. The stars were moving too fast, but only if we assumed that visible matter was all there was. Once dark matter was included, the motion made sense. An everyday comparison can help make this intuitive. Imagine watching a carousel spinning in the dark. You can only see a few horses near the centre, but the outer edge is hidden. If the horses you see are moving very fast, faster than expected, you might assume the carousel is larger and heavier than it appears. The unseen structure contributes to the motion you observe. In galaxies, stars play the role of those visible horses. Their speed reveals the size and mass of the system they belong to, even when much of that system cannot be seen directly. This realization was one of the strongest early pieces of evidence for dark matter. It did not depend on complex theory or exotic assumptions. It came from careful observation, repeated measurement, and simple gravitational reasoning. As we continue, we'll look more closely at how this mismatch between expected and observed motion became known as the missing mass problem, and why it reshaped our understanding of the universe. As evidence from galaxy rotation accumulated, scientists began to recognize that they were facing a broader issue, not just an odd behavior in a few distant systems. This issue became known as the missing mass problem. It was not a single experiment or a single observation that raised concern, but a growing pattern that appeared wherever gravity could be measured at large scales. The idea is simple to state. When astronomers add up all the visible matter in a galaxy, stars, gas, dust, and anything else that emits or absorbs light, they can calculate how much gravitational pull that matter should produce. From that calculation, they can predict how fast stars should move and how tightly systems should be bound together. But when they compare those predictions with actual observations, the numbers do not match. The observed motion consistently requires more mass than can be seen. At first, scientists approach this cautiously. Measurement errors are common in any field, especially when dealing with faint objects across immense distances. Instruments can misread signals, assumptions can be wrong. Early studies were checked, rechecked, and refined. As technology improved, so did precision, yet the discrepancy remained, and in many cases, it became even clearer. What made the missing mass problem especially compelling was that it appeared at multiple scales. It was not limited to individual galaxies. Galaxy clusters, vast collections of hundreds or even thousands of galaxies, showed the same issue. The galaxies within these clusters moved too fast to be held together by visible matter alone. According to known physics, the clusters should disperse over time. Instead, they remain bound, stable over billions of years. This consistency mattered. If the problem had appeared only in one type of system, it might have suggested a local anomaly. But when the same shortfall appeared in galaxies, clusters, and later in even larger cosmic structures, it pointed toward a universal cause. Something fundamental was missing from the inventory of matter in the universe. Another important aspect of the missing mass problem was its calm persistence. There was no sudden crisis or dramatic failure of theory. Gravity itself continued to work exactly as expected. The laws of motion remained reliable. What was missing was not understanding, but content. The equations were sound. The input, the amount of mass, it was incomplete. This distinction is important for how science progresses. When predictions fail, scientists must ask whether the laws are wrong or whether something has been overlooked. In this case, decades of evidence suggested that gravity behaved correctly. What seemed absent was a form of matter that did not announce itself through light. It's also worth noting that the missing mass problem did not demand immediate answers. Astronomers could continue to map galaxies, measure motions, and refine models, even without knowing exactly what the missing mass was made of. The problem became a stable part of astrophysics, acknowledged, studied, and gradually framed more precisely. A gentle way to think about this is to imagine balancing a scale. You place visible objects on one side and expect it to level. When it doesn't, you don't assume the scale is broken right away. You first check whether something unseen might be adding weight to the other side. The missing mass problem is that quiet imbalance, observed again and again across the universe. As we move forward, we'll look at how early astronomers first noticed this imbalance, and how the idea of missing mass slowly transformed into the modern concept of dark matter. Long before the term dark matter was widely used, astronomers were already noticing that something about the universe did not quite add up. In the early 20th century, as telescopes improved and observations extended beyond our own galaxy, scientists began to study large collections of stars and galaxies in a more systematic way. Their goal was simple: to understand how these systems were held together. One of the earliest hints came from studies of galaxy clusters. When astronomers measured the speed of galaxies moving within clusters, they found that the galaxies were travelling far too fast. If only the visible galaxies and their gas were providing gravitational pull, the cluster should have dispersed. Yet it remained stable. This suggested that there was additional mass present, contributing to the cluster's gravity. At the time, this idea was treated cautiously. Astronomy was still developing as a precision science, and many alternative explanations were considered. Perhaps the clusters were not actually stable. Perhaps they were temporary groupings that would eventually break apart. Or perhaps the measurements themselves were incomplete. Still, the same pattern appeared repeatedly, across different clusters and with different instruments. As decades passed, the focus shifted toward individual galaxies. Spiral galaxies, with their clearly defined rotating disks, became especially useful laboratories for studying motion. By measuring the speed of stars and gas at different distances from galactic centers, astronomers could test how mass was distributed. These measurements became more refined as spectroscopic techniques improved, allowing for more accurate velocity calculations. The results consistently showed that visible matter could not account for the observed motion. Even when faint stars and cold gas were included, there was still a large gap between the mass that could be seen and the mass that seemed to be required. This gap did not shrink as instruments improved. In many cases, it became more clearly defined. It's important to appreciate how gradual this realization was. There was no single moment when the scientific community collectively agreed that a new type of matter must exist. Instead, the evidence accumulated quietly, paper by paper, observation by observation. Each new study added a small piece to the same picture. During this period, astronomers also explored the possibility that ordinary matter might simply be harder to detect than expected. Perhaps there were vast numbers of dim stars, cold planets, or clouds of gas that emitted little light. Extensive surveys were conducted to search for such objects. While some hidden matter was found, it was never enough to solve the problem. What made these early measurements especially convincing was their consistency. Different research groups using different methods and observing different regions of space reached similar conclusions. The universe appeared to contain far more mass than could be accounted for by what telescopes could see. In hindsight, these early observations laid the foundation for everything that followed. They framed the problem in a way that allowed later scientists to ask more precise questions. How much mass is missing? Where is it located? And how does it behave? At the time, these questions did not demand immediate answers. Science often moves forward by clearly defining what is unknown. By the mid-20th century, astronomers had done just that. They had identified a persistent discrepancy between visible matter and gravitational effects, a discrepancy that would eventually lead to the modern concept of dark matter. As we continue, we'll focus on one of the most informative tools to emerge from this period, the study of galaxy rotation curves and how they made the missing mass impossible to ignore. To make sense of the missing mass problem, astronomers needed a clear, repeatable way to compare what they could see with how gravity behaved. This led to one of the most important tools in modern astronomy, the galaxy rotation curve. Despite the technical name, the idea behind it is straightforward and can be understood without advanced mathematics. A rotation curve is simply a graph that shows how fast stars and gas move as a function of their distance from the centre of a galaxy. Imagine starting near the bright centre of a spiral galaxy and slowly moving outward, measuring the speed of objects along the way. Each measurement adds 1 point to the curve. When connected, these points reveal how orbital speed changes with distance. If a galaxy's mass were concentrated mainly in its visible stars, the rotation curve would follow a familiar pattern. Speeds would rise near the centre, where mass is dense, and then gradually fall as distance increases and enclosed mass stops growing significantly. This is exactly what we see in systems like our solar system, where the Sun contains almost all the mass. But real galaxies do something different. Instead of declining, their rotation curves tend to flatten out. Beyond a certain distance, stars keep orbiting at nearly the same speed no matter how far they are from the centre. This behaviour is not subtle. The difference between expected and observed speeds is large and consistent. It shows up clearly in the data, even when measurements are repeated with different instruments and techniques. The meaning of a flat rotation curve is simple but powerful. It tells us that the amount of mass enclosed within a star's orbit keeps increasing, even far beyond the region where most visible stars are located. In other words, mass is spread out well beyond the bright disk of the galaxy. This extended mass does not shine. Telescopes do not see it directly, yet its gravitational influence is unmistakable. The outer stars move as if they are embedded in a much larger structure, one that extends far into what would otherwise appear to be empty space. Astronomers use these rotation curves not just to infer the existence of dark matter, but also to map its distribution. The shape of the curve reveals how mass is spread throughout the galaxy. In most cases, the data suggest a roughly spherical halo of dark matter surrounding the visible disk, dominating the galaxy's total mass. What makes rotation curves especially convincing is their universality. They are not limited to one type of galaxy or one region of the universe. Large galaxies and small ones, bright galaxies and faint ones, nearby galaxies and distant ones. The same flattened pattern appears again and again. There is also a calm reliability to this method. It does not rely on rare or extreme events. It comes from ordinary stars moving in stable orbits, measured over long periods of time. The evidence does not flicker or vanish with better data. It becomes clearer. A gentle, everyday comparison can help here. Imagine walking around a city at night and noticing that streetlights extend far beyond the crowded downtown area. Even when buildings thin out, the lights continue evenly spaced, showing that the city is larger than it first appeared. Rotation curves are like those distant lights, quietly revealing the true size of the structure. By the time astronomers fully understood rotation curves, the missing mass problem was no longer abstract. It had a clear shape, a clear scale, and a clear gravitational signature. Something unseen was present, shaping galaxies from the inside out. Next, we'll look at what this implies about galaxy stability, and why, without dark matter, many galaxies simply could not exist in the form we observe today. Once rotation curves were understood, their implications became impossible to ignore. If stars in the outer regions of galaxies are moving as fast as observations show, then gravity must be strong enough to keep them bound. Without sufficient gravitational pull, those stars would simply drift away, escaping into intergalactic space. The fact that they do not tells us something essential about how galaxies are held together. To see why this matters, it helps to think about balance. Orbital motion is a balance between two tendencies. Gravity pulls objects inward, while motion carries them forward. When these forces are matched, an object follows a stable orbit. If gravity is too weak, the object escapes. If it is too strong, the object falls inward. In a galaxy made only of visible matter, this balance fails in the outer regions. The gravitational pull from the central stars and gas drops off with distance. According to basic physics, it should not be strong enough to hold on to fast-moving outer stars. The predicted outcome is gradual disintegration. Over time, the galaxy would lose its outer material and shrink. But real galaxies do not behave this way. They maintain their shape over billions of years. Their spiral arms remain intact. Their stars follow smooth, long-lived orbits. This stability is not temporary or fragile. It is persistent, observed across cosmic history. The only way to explain this stability within known physics is to add more mass. This mass must be distributed in such a way that gravity remains strong even far from the galaxy's bright center. Dark matter provides exactly this. Its extended halo increases the total gravitational pull without adding light. This idea also helps explain why galaxies form the way they do. During their early development, gas and dust would not have been able to collapse into stable structures without sufficient gravitational scaffolding. Dark matter provides that scaffolding, allowing galaxies to grow gradually instead of dispersing. It's worth emphasizing that this conclusion does not depend on a single assumption. Astronomers test galaxy stability using simulations, mathematical models, and observations across time. When dark matter is included, models produce galaxies that look and behave like the ones we see. When it is excluded, galaxies become unstable or fail to form properly. A calm comparison can make this clearer. Imagine a spinning ice skater holding a heavy backpack. The added mass helps stabilize the motion. If the backpack suddenly vanished while the skater continued spinning at the same speed, balance would be lost. In galaxies, dark matter plays a stabilizing role, quietly anchoring motion that would otherwise become chaotic. Another way to see this is through longevity. Many galaxies we observe today are billions of years old. They have survived collisions, interactions, and internal changes. Without an additional source of gravity, they would not have remained intact for such long spans of time. This stability tells us something reassuring about the universe. Large structures are not fragile accidents. They are supported by underlying mass distributions that make long-term order possible. Dark matter is part of that hidden support. As we continue, we'll take a closer look at what the word dark really means in this context, and why it refers specifically to light, not to danger, mystery, or emptiness. At this point, it's helpful to slow down and clarify a word that carries a lot of weight: dark. In everyday language, dark can suggest danger, mystery, or absence. In science, however, the word is used much more narrowly and much more carefully. When scientists say dark matter, they're not describing something ominous or unknowable. They're describing a very specific physical property: the lack of interaction with light. Light is how most of astronomy works. Telescopes collect photons, tiny packets of light, that have travelled across space. From that light, astronomers learn about temperature, composition, motion, and distance. Stars shine because nuclear reactions produce light. Gas clouds glow or absorb light depending on their energy. Dust blocks and scatters light. Almost everything we know about the universe comes from these interactions. Dark matter does none of this. It does not emit light at any wavelength we can detect. It does not reflect light from nearby stars. It does not absorb light passing through it. If a cloud of dark matter were floating between Earth and a distant galaxy, our telescopes would see straight through it. The galaxy would appear unchanged. This is the entire reason dark matter is called dark. Not because it is hidden on purpose, not because it is mysterious by nature, simply because it does not couple to the electromagnetic force, the force responsible for light. This distinction matters because it prevents misunderstandings. Dark matter is not a shadow. It is not black smoke drifting through space. It is not the absence of matter. It is matter that exists, has mass and exerts gravity, but remains invisible to our most common detection method. There are good physical reasons why this might be the case. In the universe, different forces govern different interactions. Ordinary matter interacts through gravity, electromagnetism, and nuclear forces. Dark matter, as far as we can tell, interacts primarily through gravity, and possibly through very weak interactions that are difficult to detect. If it lacks electromagnetic interaction, then light simply passes by without noticing it. This idea may feel unfamiliar, but it is not unprecedented. Neutrinos, for example, are particles that pass through Earth in enormous numbers every second, barely interacting with anything. They are not dark matter in sufficient quantity, but they demonstrate that invisibility does not imply non-existence. Nature allows particles to be subtle. Another important clarification is that dark matter is not hidden because it is far away. It exists everywhere in the universe, including within and around our own galaxy. Its invisibility is not due to distance or faintness. Even if it were right next to us, it would still be dark in the same way. Understanding this helps keep the discussion grounded. Dark matter is not a placeholder for ignorance. It is a description of behaviour. We observe gravitational effects that demand additional mass. We observe no corresponding light. The simplest explanation is matter that does not interact with light. This also explains why dark matter was not discovered in a laboratory first. Most laboratory experiments rely on electromagnetic signals. If something does not produce those signals, it can go unnoticed for a long time. In this case, the universe itself became the experiment. Galaxies and clusters provided the evidence long before detectors on Earth could hope to find it directly. So when we say dark, we're really saying non-luminous. It is a technical term, calm and precise. It tells us what dark matter does not do, not what it is made of or where it came from. Those questions come later. For now, it's enough to rest with this clarity. Dark matter is not invisible because it is unreal. It is invisible because light is not the language it speaks. After clarifying what dark means, the next common misunderstanding is about absence. If dark matter cannot be seen, touched, or detected by light, it can be tempting to imagine it as nothing at all, as empty space. But dark matter is not emptiness. It is not a gap. It is not the absence of matter. In fact, its defining feature is that it adds mass to the universe. Empty space, even in modern physics, is not truly empty. It has energy, fluctuations, and structure at very small scales. But empty space does not behave like mass in the way dark matter does. It does not clump into halos around galaxies. It does not pull stars into stable orbits. It does not hold galaxy clusters together through gravity. Dark matter does all of these things. This distinction matters because it tells us how dark matter behaves. Dark matter gathers, it accumulates, it forms large, extended structures that shape the motion of visible matter. These behaviors are not properties of empty space, they are properties of something that has weight, something that contributes to gravity in a measurable way. When astronomers map the distribution of mass in galaxies and clusters, they find that most of the gravitational pull comes from regions where there is very little visible matter. These regions are not voids, they are filled with dark matter. The gravity there is strong, steady and predictable. Stars orbit within it. Galaxies move through it. Light bends around it. One way scientists confirm that dark matter is not empty space is through gravitational lensing. When light from a distant object passes near a massive structure, its path bends. This bending depends only on mass, not on light emission. When astronomers observe lensing in regions where little visible matter exists, they can still measure strong gravitational effects. This tells us that something with mass is present, even though it cannot be seen. Another important clue comes from how dark matter behaves during collisions between galaxy clusters. In some cases, visible matter, especially hot gas, slows down and interacts, while dark matter passes through largely unaffected. The gravitational influence moves ahead of the visible material. This separation would not happen if the mass was simply empty space or a property of light. It happens because dark matter behaves like a form of matter that interacts weakly but still has mass. It's also helpful to consider what would happen if dark matter were truly nothing. If galaxies were embedded in emptiness, there would be no additional gravitational pull beyond what visible matter provides. Rotation curves would decline, clusters would disperse, large-scale structure would look very different from what we observe. The universe would be far less organized. Instead, we see a universe with a clear underlying structure. Galaxies trace long filaments. Clusters sit at intersections. Motion follows patterns that persist over billions of years. This order requires mass, real, distributed and stable mass. A simple, everyday comparison can help. Imagine standing in a room filled with clear, still air. Air is mostly invisible, but it has mass. It exerts pressure. It resists motion. If the room were truly empty, sound would not travel. Pressure would vanish, and movement would feel very different. Invisibility does not mean absence. It means interaction is limited. Dark matter is similar in that sense, though far more subtle. It does not interact through light or touch, but through gravity alone. That single interaction is enough to shape the largest structures in the universe. Understanding that dark matter is not empty space helps anchor the discussion. We're not talking about a trick of perception or a gap in measurement. We're talking about something real, with mass, quietly present everywhere galaxies exist. Next, we'll address another common source of confusion by clearly separating dark matter from a different concept that is often mentioned alongside it: dark energy. As the term dark matter became more widely known, another concept entered public discussion with a similar name: dark energy. Because both include the word dark, they're often confused or blended together. In reality, they refer to very different things, with very different roles in the universe. Taking a moment to separate them clearly helps keep the rest of the discussion grounded. Dark matter, as we've seen, behaves like matter. It has mass, it responds to gravity, it gathers around galaxies and clusters, helping to hold them together and shape their motion. Its effects are strongest where matter is concentrated, and it plays a major role in the formation of cosmic structures. Dark energy behaves in almost the opposite way. Dark energy does not clump, it does not form halos or clusters. Instead, it appears to be spread evenly throughout space. Its main observable effect is not on the motion of stars within galaxies, but on the expansion of the universe itself. Observations show that the expansion of the universe is accelerating, and dark energy is the name given to whatever is causing that acceleration. This distinction is important. Dark matter pulls inward through gravity. Dark energy, as far as we can tell, pushes outward by influencing the expansion of space. They are not two sides of the same phenomenon. They solve different problems and are supported by different types of evidence. Another way to keep them separate is to notice when and where their effects appear. Dark matter shows its influence on relatively small scales, within galaxies and clusters. Dark energy becomes noticeable only on the larger scales, across the universe as a whole. If dark energy were removed, galaxies would still rotate the way they do. If dark matter were removed, galaxies would struggle to exist at all. It's also worth noting that the word dark is used in both cases for the same basic reason: invisibility to light. Dark energy does not emit or absorb light either, but beyond that shared label, the similarities largely end. Scientists study dark matter and dark energy using different tools and methods. Dark matter is inferred through gravitational effects like rotation curves and lensing. Dark energy is inferred through measurements of cosmic expansion, such as distant supernova and the large-scale distribution of galaxies. Mixing the two concepts can make both harder to understand. A gentle comparison may help. Imagine a city at night. Dark matter is like the unseen support beams and foundations that hold buildings together. Dark energy is like a gradual stretching of the city's layout over time, increasing the distance between neighborhoods without affecting the buildings themselves. Both are invisible, but they influence the city in very different ways. Clarifying this difference allows us to focus more precisely on dark matter itself. When we talk about dark matter, we are not trying to explain cosmic expansion or acceleration. We're trying to account for missing mass and unexpected gravity. Keeping that focus makes the science clearer and calmer. As we continue, we'll look at how much dark matter actually exists, and how scientists have been able to estimate its abundance in the universe without ever seeing it directly. Once scientists accepted that dark matter was real and widespread, the next question became quantitative. How much of it is there? Answering this does not require knowing what dark matter is made of. Instead, it relies on carefully measuring how strongly gravity acts across different parts of the universe, and comparing that with how much visible matter is present. One of the most reliable ways to estimate the total amount of matter in the universe comes from studying large-scale cosmic patterns. These patterns include how galaxies are distributed, how galaxy clusters form, and how matter clumps over time. When scientists run simulations of the universe using different amounts of matter, only certain values reproduce the structures we actually observe. These studies consistently point to the same result. Ordinary matter, the atoms that make up stars, planets, gas, and living beings, accounts for only a small fraction of the universe's total mass. Dark matter makes up a much larger share. In simple terms, for every unit of visible matter, there are several units of dark matter shaping the same region of space. Another independent line of evidence comes from the early universe. The faint background radiation left over from shortly after the Big Bang carries subtle patterns that reflect the balance of matter at that time. By analysing these patterns, scientists can determine how much matter existed and how it was distributed. These measurements agree closely with estimates based on galaxies and clusters today. What's striking is how consistent these results are across different methods. Whether scientists look at nearby galaxies, distant clusters, or the universe when it was very young, they arrive at nearly the same proportions. This consistency adds confidence. It suggests that dark matter is not a local phenomenon or a temporary effect, but a fundamental component of the cosmos. To keep the numbers gentle and intuitive, it's often helpful to think in ratios rather than exact percentages. Imagine the total matter content of the universe as a small collection of objects on a table. Only a small portion would be familiar visible matter. Most of what's there would be dark matter, present, heavy, and influential but unseen. It's also important to note what these estimates do not include. They refer only to matter, not to dark energy, which dominates the universe's overall energy content. When scientists talk specifically about matter, the stuff that clumps and forms structures, dark matter clearly outweighs everything else. This imbalance explains why dark matter has such a strong influence on cosmic evolution. It sets the gravitational landscape long before stars ignite or galaxies fully form. Visible matter follows paths carved out by dark matter, settling into wells of gravity that already exist. A calm reflection here is that the universe we see is not built primarily from what shines. Light traces only a small fraction of what is there. Most of the structure comes from something quieter, something that shapes motion without ever announcing itself through brightness. As we move on, we'll look at one of the strongest observational confirmations of dark matter's existence beyond individual galaxies, the behaviour of entire clusters of galaxies, where gravity reveals hidden mass on truly enormous scales. Galaxy clusters are among the largest gravitationally bound structures in the universe. They contain hundreds or even thousands of individual galaxies, along with vast amounts of hot gas spread between them. Because of their size and complexity, clusters offer an especially clear view of how gravity operates on large scales. And once again, when scientists measure that gravity, they find more mass than light can explain. One of the simplest ways to see this is by measuring how fast galaxies move within a cluster. Each galaxy orbits the cluster's centre of mass, influenced by the combined gravity of everything else inside. By observing these motions, astronomers can estimate the total mass required to keep the cluster bound. When they add up the mass of all visible galaxies and gas, they consistently come up short. The gap is not small. In many clusters, visible matter accounts for only a fraction of the mass needed. The remaining gravitational pull must come from something unseen. This conclusion was reached early in the study of galaxy clusters and has only grown stronger with better data. Clusters also contain enormous amounts of hot gas that glow in X-rays. This gas often outweighs the galaxies themselves in terms of visible mass. Even after including this gas, however, the missing mass problem remains. The gas is hot enough that, without sufficient gravity, it would escape the cluster. Its presence and temperature provide another independent measure of the cluster's total mass, and again, the numbers point toward dark matter. What makes galaxy clusters especially compelling is that they provide multiple overlapping lines of evidence. Scientists can measure galaxy speeds, gas temperature, and gravitational lensing all within the same system. Each method relies on different physics, yet they all converge on the same conclusion. There is far more mass present than can be seen. Gravitational lensing is particularly powerful here. As light from distant background galaxies passes through a cluster, its path bends due to the cluster's gravity. By studying the distortions in these background images, astronomers can map the cluster's mass distribution directly. These maps reveal massive regions where little visible matter exists, and where dark matter must dominate. In some clusters, the separation between visible matter and dark matter becomes especially clear. When clusters collide, the hot gas interacts and slows down, while galaxies and dark matter continue moving with less resistance. The gravitational mass, traced through lensing, follows the dark matter rather than the visible gas. This behaviour is difficult to explain without invoking a form of matter that interacts weakly, but carries most of the mass. Clusters, in this sense, act like natural laboratories. Their size amplifies gravitational effects, making discrepancies easier to measure and harder to dismiss. They show that dark matter is not just a feature of individual galaxies, but a fundamental component of the universe's larger structures. A gentle way to think about this is to imagine watching a flock of birds from far away. You may not see the wind, but when every bird responds in the same way, you can infer its presence. In galaxy clusters, the coordinated motion of galaxies and the bending of light reveal an invisible influence shaping everything at once. As we continue, we'll explore one of the most elegant tools for studying this invisible influence in more detail: gravitational lensing itself, and how it allows scientists to see dark matter without light. Gravitational lensing is one of the most direct and quietly powerful ways scientists study dark matter. It does not rely on how fast stars move or how hot gas becomes. Instead, it uses light itself as a probe of gravity. Even though dark matter does not interact with light, gravity always does, and that interaction leaves a clear, measurable signature. According to general relativity, mass bends space. When light travels through curved space, its path bends as well. This means that a massive object like a galaxy or a galaxy cluster can act like a lens. Light from distant background objects passes near the mass, curves slightly, and reaches us from a different direction. The result can be subtle distortions, stretched shapes, or, in extreme cases, arcs and multiple images of the same object. What makes gravitational lensing so valuable is that it depends only on mass. It does not matter whether that mass is bright, faint, hot, cold, or completely invisible. If mass is present, lensing will reveal it. This makes lensing an ideal tool for studying dark matter. Astronomers observe lensing by carefully analysing images of distant galaxies. Many of these galaxies appear slightly stretched or skewed, not because of their own shape, but because their light has passed through intervening mass. By studying these distortions statistically across large regions of the sky, scientists can reconstruct maps of mass distribution. When these mass maps are compared to images of visible matter, a clear pattern emerges. The regions with the strongest gravitational influence often do not align with where the most light is coming from. Instead, large amounts of mass appear to be spread out in areas with few stars or galaxies. This mismatch is exactly what we expect if dark matter dominates the mass budget. Gravitational lensing also works on different scales. Strong lensing, which produces dramatic arcs and multiple images, reveals the mass of dense regions like galaxy clusters. Weak lensing, which involves very small distortions, reveals the large-scale structure of dark matter across vast cosmic distances. Both methods tell the same story. One of the most important aspects of lensing is its independence. It does not rely on assumptions about how matter moves or how it behaves internally. It simply measures how much gravity is present and where. Because of this, lensing provides some of the strongest evidence that dark matter is real and spatially distributed. A calm way to picture this is to imagine looking through a piece of clear glass that is slightly uneven. You cannot see the glass itself, but the background scene appears warped. From that warping alone, you can infer the shape of the glass. In the universe, dark matter is like that invisible glass, shaping the path of light without ever revealing itself directly. Gravitational lensing also helps answer where dark matter is located. It shows that dark matter forms large halos around galaxies and clusters, extending far beyond visible edges. It traces filaments connecting structures across the universe, outlining a vast invisible framework. As we move on, we'll look at how scientists use this lensing information to create detailed maps of the invisible, turning subtle distortions of light into a clearer picture of dark matter's structure. Once gravitational lensing revealed that unseen mass was shaping the universe, scientists began using it not just as evidence, but as a tool for mapping. The goal was no longer simply to confirm that dark matter exists, but to understand where it is and how it is arranged across space. This marked a quiet shift in perspective. Dark matter moved from being a missing ingredient to being a structural framework. Mapping dark matter requires patience. The distortions caused by weak gravitational lensing are extremely subtle. Individual galaxies may appear only slightly stretched or tilted, changes so small that they are invisible to the eye. To extract meaningful information, astronomers analyze the shapes of millions of galaxies at once, looking for tiny statistical patterns. Over large areas of the sky, these patterns reveal how mass is distributed. When these analyses are completed, the resulting maps show something remarkable. Dark matter is not scattered randomly. It forms long filaments, dense knots, and extended halos. Galaxies tend to sit within these knots, and clusters form where filaments intersect. This network is often called the cosmic web, and it represents the large-scale structure of the universe. What's important here is that the visible universe appears to follow this invisible structure. Galaxies trace the same patterns outlined by dark matter. Where dark matter is dense, galaxies are more likely to form and persist. Where it is sparse, space tends to remain relatively empty. In this way, dark matter acts as a kind of gravitational blueprint. These maps also show that dark matter halos are much larger than the galaxies they surround. A galaxy's visible stars may occupy only a small central region, while its dark matter halo extends many times farther outward. Stars orbit within these halos, responding to gravity from matter they cannot see. Another calm but important insight comes from comparing maps at different distances. Because light takes time to travel, looking farther into space also means looking further back in time. By mapping dark matter at different epochs, scientists can see how structure has evolved. The same filamentary patterns appear early in the universe and gradually become more pronounced over billions of years. This slow growth matches predictions based on dark matter's behaviour. Mapping the invisible also helps test theories about what dark matter might be. Different types of dark matter would produce slightly different structures. Some would smooth out small-scale features, while others would allow them to persist. By comparing observations with simulations, scientists can narrow down which possibilities remain plausible. A gentle way to think about these maps is to imagine a city seen only through traffic patterns. Even without seeing the roads directly, you could infer where highways, intersections, and neighbourhoods are located. Dark matter maps work in a similar way. They reconstruct the underlying structure from how light and galaxies move through it. What emerges from all of this is a universe that is deeply organised, even when most of its mass is invisible. Dark matter is not just an extra component added to fix equations. It is the scaffolding that allows the visible universe to take shape at all. As we continue, we'll move further back in time and explore the role dark matter played in the early universe, when the first structures were just beginning to form. To understand dark matter fully, it helps to look not just at where it is now, but at when its influence first became important. That takes us back to the early universe, long before stars, galaxies, or planets existed. At that time, the universe was hot, dense, and nearly uniform. Small differences in density existed, but they were extremely subtle. In this early phase, ordinary matter behaved very differently from dark matter. Ordinary matter interacted strongly with radiation. Photons pushed on particles, keeping matter hot and smooth. This interaction prevented ordinary matter from clumping easily. Any small region that tried to grow denser was quickly smoothed out by pressure and radiation. Dark matter did not experience this resistance. Because dark matter does not interact with light, it was free to respond only to gravity. As the universe expanded and cooled, dark matter began to clump very slowly, guided by tiny initial density variations. These clumps were small at first, but gravity amplified them over time. Where dark matter gathered, its gravitational pull became slightly stronger, drawing in more dark matter. This difference in behaviour gave dark matter a quiet head start. While ordinary matter was still tightly coupled to radiation, dark matter was already forming the earliest gravitational wells. These wells were not visible. There were no stars or glowing gas clouds yet, but the structure was there, forming the foundation for everything that followed. Eventually, as the universe cooled further, radiation loosened its grip on ordinary matter. At that point, gas could begin to fall into the gravitational wells created by dark matter. Where dark matter had gathered, ordinary matter followed. Gas accumulated, compressed, and heated. Over time, the first stars ignited within these regions. This sequence is important because it explains why structure exists at all. Without dark matter, ordinary matter alone would have struggled to form galaxies within the available time. The universe would be smoother, more diffuse, and far less structured. Dark matter made early structure formation efficient enough for galaxies to appear. Evidence for this process comes from several sources. Observations of the cosmic background radiation show tiny fluctuations that match predictions of dark matter-driven growth. Computer simulations that include dark matter reproduce the large-scale structure we see today. Simulations without dark matter fail to do so. What's striking is how gentle this process is. Dark matter does not violently reshape the universe. It does not create light or explosions. It simply deepens gravitational wells over long periods of time. Structure grows slowly, guided by gravity acting on something we cannot see. A calm way to picture this is to imagine a landscape forming under snow. The contours of hills and valleys exist long before the snow melts. When it does, water flows along paths that were already shaped. In the universe, dark matter formed the contours first. Ordinary matter later revealed them. As we move on, we'll look more closely at how this invisible framework guided the formation of galaxies and larger structures, and why visible matter tends to trace dark matter so closely even today. With dark matter shaping the early universe, the next step is to understand how this invisible component guided the formation of the structures we see today. Structure formation refers to the gradual process by which small irregularities in the early universe grew into galaxies, clusters, and the vast cosmic web. At the beginning, the universe was remarkably uniform. Density differences were tiny, often less than 1 part in 100,000. On their own, such small variations would not have been enough to produce the complex structures we observe. Dark matter changed this by amplifying those initial differences through gravity. Wherever there was a slightly higher concentration of dark matter, gravity pulled in more dark matter from nearby regions. This process happened slowly and steadily, over hundreds of millions of years. As these regions grew denser, their gravitational pull strengthened, making them even more effective at gathering material. Ordinary matter followed a different path at first. While the universe was hot, gas remained smooth and resisted collapse. But as time passed and temperatures dropped, gas could respond more easily to gravity. When it did, it flowed into the dark matter concentrations that already existed. This created a layered structure. Dark matter formed large, extended halos. Within those halos, gas cooled, condensed, and eventually formed stars and galaxies. The visible universe emerged as a kind of tracer, outlining the underlying dark matter distribution. Simulations help make this process clear. When scientists model the universe with dark matter included, small fluctuations grow into filaments and clusters that closely resemble what we observe. Galaxies line up along these filaments, forming networks that stretch across vast distances. When dark matter is removed from these simulations, structure formation stalls. The universe remains too smooth. This agreement between simulation and observation is one of the strongest arguments for dark matter. It shows not just that dark matter exists, but that its behavior matches what is needed to build the universe we see. Another important feature of structure formation is its timescale. Nothing happens quickly. Galaxies do not appear all at once. They grow through gradual accretion, mergers, and slow evolution. Dark matter supports this calm progression by providing long-lived gravitational wells. A gentle comparison is to imagine dew forming on grass in the early morning. Tiny variations in surface texture determine where droplets gather first. Over time, those small differences become visible patterns. Dark matter plays a similar role, guiding accumulation without drawing attention to itself. Understanding structure formation also helps explain why dark matter remains relevant today. It did not disappear once galaxies formed. It continues to shape their motion, influence their interactions, and maintain stability over cosmic time. As we move forward, we'll focus more closely on the relationship between dark matter and ordinary matter, and why visible material so often appears to follow paths set by something it cannot see. Once galaxies and larger structures began to form, a clear relationship emerged between dark matter and the matter we can see. Again and again, observations show that ordinary matter tends to settle where dark matter already exists. This is not a coincidence, and it does not require any special interaction between the two. Gravity alone is enough to explain it. Dark matter forms large, stable gravitational wells. These wells are deep compared to what ordinary matter could create on its own, especially in the early universe. When gas begins to cool and move freely, it naturally falls toward regions of stronger gravity. Since dark matter dominates the mass, it dominates the gravitational landscape. Ordinary matter responds by following those contours. This process continues long after the first galaxies form. Gas flows into dark matter halos, feeding star formation. When galaxies collide or merge, their dark matter halos interact first, guiding how the visible components rearrange. Even when gas is blown outward by stellar winds or energetic events, gravity eventually draws much of it back toward the same dark matter-dominated regions. An important point here is that dark matter does not pull ordinary matter through any special force. There is no attraction unique to dark matter. Both respond to gravity in exactly the same way. The difference is simply quantity. Because there is so much more dark matter, it sets the stage. This explains why maps of dark matter and maps of galaxies look so similar. Where dark matter density is high, galaxies are common. Where it is low, space is relatively empty. The visible universe traces the invisible one. There are also situations where this relationship becomes especially clear. In some galaxy cluster collisions, the visible gas can be slowed down by interactions, while dark matter passes through with little resistance. After the collision, galaxies and dark matter continue ahead, while gas lags behind. The separation reveals which component is shaping the gravitational field. Time and again, it is the dark matter. On smaller scales, the same principle applies. Within individual galaxies, stars orbit within dark matter halos. Their paths reflect the combined gravity of both visible and invisible mass, but the invisible component dominates at larger distances. A calm, everyday comparison can help here. Imagine rainwater flowing across land. The water does not create the landscape, it follows it. Valleys and slopes determine where water gathers and how it moves. Dark matter is like that landscape. Ordinary matter is the water, revealing the shape that was already there. This relationship also helps explain why dark matter is so difficult to detect directly. Ordinary matter clumps into dense objects like stars and planets, where interactions are frequent. Dark matter remains more diffuse, spread across large regions. Its influence is strongest collectively, not locally. Understanding why normal matter follows dark matter helps unify many observations. It explains galaxy shapes, cluster behavior, and large-scale patterns without adding unnecessary complexity. Gravity, acting patiently over time, is enough. As we continue, we'll begin narrowing the question. If dark matter is real and widespread, what is it not made of? The next step is to rule out familiar possibilities. As evidence for dark matter accumulated, scientists naturally began asking a more specific question. If this unseen matter is so abundant, could it simply be made of familiar things that are hard to detect? Before proposing new particles or new physics, researchers worked carefully through every ordinary possibility. This process of elimination is an important part of how science stays grounded. One of the first ideas was that dark matter might consist of faint stars. Not all stars shine brightly. Some are small, cool, or old, producing very little light. Perhaps galaxies contained vast populations of these dim stars, adding mass without much brightness. Astronomers searched for this possibility by studying starlight carefully and counting stars across different wavelengths. The results were clear. While faint stars exist, there are nowhere near enough of them to account for the missing mass. Another idea focused on gas and dust. Gas can be cold and difficult to detect, especially if it does not glow strongly. Dust can block light rather than emit it. Scientists measured gas using radio waves and X-rays, and they mapped dust by its effect on background light. These surveys showed that gas and dust do contribute mass, but again, not nearly enough. Even when all detectable gas is included, the mass shortfall remains large. Planets were also considered. Could dark matter be made of countless rogue planets drifting through galaxies? These objects would be cold, dark, and hard to see. To test this, astronomers used a technique called gravitational microlensing, watching for brief flashes of light as compact objects pass in front of distant stars. The frequency of these events revealed how many such objects exist. The answer was consistent. Planets and similar bodies exist, but they cannot make up more than a small fraction of dark matter. Black holes were another candidate. Because black holes do not emit light directly, they seem like a natural fit at first glance. However, black holes still interact strongly with their surroundings. They affect nearby stars, heat gas, and leave detectable signatures. Large numbers of black holes would alter galaxies in ways we do not observe. While some black holes may contribute to the total mass, they cannot account for most of it. All of these possibilities fall under a category sometimes called ordinary dark matter, matter made of familiar particles arranged in hard-to-see ways. One by one, careful observation has ruled out these options as the main explanation. The conclusion is not dramatic, but it is firm. Dark matter cannot be mostly made of atoms, stars, gas, planets, or black holes. This realization marks an important turning point. If dark matter is not built from the same components as ordinary matter, then it must be something fundamentally different, not just hidden, but new. New in the sense that it does not belong to the standard collection of particles that make up everyday reality. There is a quiet discipline in this process. Scientists did not leap to exotic explanations immediately. They exhausted the familiar first. Only when those paths failed did the idea of new particles become necessary. A gentle way to rest with this idea is to notice how careful elimination sharpens understanding. Knowing what something is not can be just as informative as knowing what it is. In this case, it narrows the field and prepares us for the next step, considering what kinds of new particles might explain dark matter's behaviour. As we continue, we'll look at early hypotheses involving massive compact objects and why they were tested so thoroughly before being set aside. Before scientists seriously considered entirely new kinds of particles, they explored a category of ideas that stayed closer to known physics. These ideas grouped potential dark matter candidates under a name that sounds informal but served a clear purpose: MASHOs, short for massive astrophysical compact halo objects. The name describes what they were thought to be: large, heavy objects made of ordinary matter hiding in the outer regions of galaxies. MACHOs included things like faint stars, brown dwarfs, rogue planets, and other compact objects that emit little or no light. The reasoning was careful and reasonable. If a galaxy's halo were filled with huge numbers of such objects, they could add significant mass without contributing much visible light. Gravity would still feel their presence, even if telescopes did not. This idea had an advantage: it did not require new physics. It used objects already allowed by known laws, simply arranged in a way that made them difficult to detect. Because of that, MACHOs were taken seriously and tested thoroughly. The main tool used to search for MACHOs was gravitational microlensing. When a compact object passes directly in front of a distant star, its gravity briefly bends and focuses the star's light, making it appear slightly brighter for a short time. The effect is subtle, but measurable. By monitoring millions of stars over long periods, astronomers could count how often these events occurred. If machos made up most of the dark matter in a galaxy, microlensing events should have been common. The galaxy's halo would be full of compact objects constantly passing in front of background stars. Observatories set up long-term surveys to watch for these tiny flashes of brightening, patiently collecting data year after year. The results were clear and consistent. Microlensing events did occur, but far less frequently than would be required if machos were the main component of dark matter. The number of detected events placed strong limits on how many compact objects could exist in galactic halos. Those limits showed that machos could account for only a small fraction of the missing mass. This outcome did not depend on a single experiment. Multiple independent surveys reached similar conclusions. Different regions of the sky were studied. Different populations of stars were monitored. Each time the data pointed in the same direction. Ordinary compact objects were not abundant enough. There were also other problems with the macho idea. Large numbers of compact objects would affect galaxies in observable ways. They would disturb stellar orbits, heat galactic disks, and leave signatures in the motion of stars. These effects are not seen at the levels required. Gradually, the scientific community moved on. Machos were not ruled out entirely. Some exist, and they contribute a small amount of mass. But they could not solve the missing mass problem. The idea had been tested carefully and set aside without drama. This moment is important because it marks a shift in thinking. When familiar objects fail to explain observations, science becomes open to unfamiliar possibilities. The failure of machos did not create confusion, it created clarity. It narrowed the search. A calm reflection here is that science advances not just by discovering new things, but by learning which paths do not lead forward. Each eliminated option makes the remaining picture sharper. By the time machos were ruled out as the main solution, the conclusion was becoming unavoidable. Dark matter is not made of ordinary matter in any hidden form. This realization opened the door to a new class of ideas, ones involving particles that interact very weakly, or perhaps not at all, with light and ordinary matter. In the next part, we'll begin exploring those possibilities, starting with the basic idea that dark matter may be made of entirely new particles. Once ordinary matter and compact objects were ruled out, the idea that dark matter might be made of new particles became not just possible, but necessary. This did not mean abandoning known physics entirely. Instead, it meant extending it carefully, guided by the specific behaviours dark matter must have. From observation alone, scientists already knew several key properties. Dark matter must have mass, because it contributes to gravity. It must be stable over billions of years because it still exists today. And it must interact very weakly with ordinary matter and light, otherwise it would have been detected already. These constraints narrow the field considerably. In particle physics, matter is made of fundamental particles that interact through known forces. Ordinary matter interacts through electromagnetism, which is why atoms form, light is emitted, and chemistry exists. Dark matter, however, appears to lack this interaction. That single difference explains much of its invisibility. The simplest particle candidates for dark matter are ones that interact through gravity, and perhaps one other very weak force, but not through electromagnetism. Such particles would pass through ordinary matter almost without effect. Trillions could move through your body every second without leaving a trace. This may sound strange, but physics already includes particles with similar behaviour. Neutrinos are a familiar example. They have very small mass and interact extremely weakly. They stream through Earth in vast numbers, barely interacting with atoms. Neutrinos themselves cannot explain dark matter fully, because they are too light and too fast. but they demonstrate that nature allows subtle particles to exist. When scientists consider dark matter particle candidates, they often begin with general categories rather than specific names. How heavy is the particle? How fast does it move? How strongly does it interact, if at all, with known particles? These questions shape how dark matter would behave in the universe. Heavier particles tend to move more slowly. Slower particles clump more easily under gravity. This turns out to be important for structure formation. If dark matter particles move too fast, they would smooth out small structures, preventing galaxies from forming as we observe them. This consideration immediately rules out many possibilities. Another important factor is stability. Dark matter must not decay quickly into other particles. If it did, its gravitational influence would change over time in ways we do not observe. Whatever dark matter is made of, it must persist quietly across cosmic history. At this stage, it's useful to notice how restrained this reasoning is. Scientists are not guessing wildly. They are letting observation define the rules. Only particles that fit all the gravitational, structural, and temporal constraints remain plausible. A calm way to think about this is to imagine narrowing down the identity of an unseen animal by its footprints. You may not know exactly what it looks like, but you can rule out many possibilities by size, weight, and movement. Dark matter's footprints are written in gravity. In the next part, we'll look more closely at one of the most important characteristics of these hypothetical particles, how weakly they interact, and why that weakness explains both their invisibility and the difficulty of detecting them. One of the most consistent features that dark matter must have is weak interaction. This phrase sounds technical, but its meaning is simple. Dark matter does not bump into ordinary matter very often. It does not stick, slow down, heat up, or light up in any noticeable way when it passes through atoms. Gravity affects it, and it affects gravity, but beyond that, its interactions are minimal. This weakness explains several things at once. It explains why dark matter is invisible to telescopes. It explains why it can pass through stars, planets, and even entire galaxies without leaving obvious traces, and it explains why detecting it directly has been such a challenge, despite decades of effort. In everyday life, interaction is how we notice things. We feel air because air molecules collide with our skin. We see objects because light reflects off their surfaces. We hear sound because vibrations travel through matter. If something does not interact through these familiar channels, it can exist all around us without being noticed. Dark matter appears to be like this. If dark matter particles pass through Earth, they do so almost silently. They do not ionize atoms, do not emit light, and do not trigger chemical reactions. Their presence is felt only through the collective effect of gravity, spread across enormous distances. This idea might seem extreme, but it fits naturally into modern physics. The universe already contains forces that operate very differently from one another. Electromagnetism is strong and noticeable at small scales. Gravity is weak by comparison, yet it dominates at large scales because it always adds up and never cancels out. Dark matter appears to live in this quiet regime, where effects are subtle locally but powerful collectively. The phrase weakly interacting does not necessarily mean non-interacting. Some theories suggest that dark matter may interact with ordinary matter through forces even weaker than the weak nuclear force, or through interactions that occur only under very specific conditions. These interactions would be rare, brief, and extremely difficult to measure. This weakness has an important consequence for cosmic history. Because dark matter does not collide or lose energy easily, it does not collapse into dense objects like stars or planets. Instead, it remains spread out in large halos. This smooth, extended distribution is exactly what observations require to explain galaxy rotation and cluster behavior. A calm comparison can help here. Imagine a vast school of fish that barely notice one another. They move through the water, influenced mainly by the overall flow rather than by collisions between individuals. Over time, their collective motion shapes large patterns, even though individual interactions are rare. Dark matter behaves similarly, responding to gravity while largely ignoring everything else. Weak interaction also explains why dark matter is so hard to study in laboratories. Most detectors rely on interactions, tiny collisions, flashes of light, or electrical signals. If dark matter rarely produces these effects, experiments must be extraordinarily sensitive and shielded from background noise. Even then, detections, if they occur, are expected to be extremely rare. This is not a failure of technology or imagination. It is a natural consequence of the properties dark matter must have to match what we see in the universe. Its quiet nature is not accidental. It is essential. As we continue, we'll examine a specific known particle that fits some of these criteria, neutrinos, and explore why, despite their weak interaction, they cannot fully explain dark matter on their own. Among the particles already known to physics, neutrinos often come up when discussing dark matter. At first glance, they seem like a natural candidate. Neutrinos have mass. Even if it is very small, they interact extremely weakly with ordinary matter, and they are abundant, produced in enormous numbers by stars, supernovae, and nuclear reactions throughout the universe. Every second, trillions of neutrinos pass through your body without you noticing. They move through Earth as if it were nearly transparent. This alone shows that invisibility and weak interaction are not unusual features in nature. Neutrinos prove that particles can exist everywhere and remain almost undetectable. Because of this, scientists carefully examined whether neutrinos could account for dark matter. The problem is not that neutrinos are too strange, it's that they are too light and too fast. Neutrinos move at speeds close to the speed of light, especially in the early universe when everything was hotter and denser. Particles that move this quickly do not clump easily under gravity. Instead of settling into small structures, they tend to stream out of dense regions, smoothing things out. This behaviour is known as hot dark matter. Observations of the universe strongly constrain how much hot dark matter can exist. The structures we see, galaxies, clusters, and smaller scale features, require matter that can clump efficiently on relatively small scales. If most dark matter were made of fast-moving particles like neutrinos, the universe would look much smoother than it does. Small galaxies would struggle to form. Fine structure would be erased. Measurements confirm this. Neutrinos do contribute a small amount to the total mass of the universe, but their contribution is limited. Their masses are simply too low to account for the missing mass inferred from gravity. Even if all neutrinos were counted, they would make up only a small fraction of what dark matter must be. This conclusion is supported by multiple lines of evidence. Particle physics experiments constrain neutrino masses. Cosmological observations constrain how fast matter could move in the early universe without disrupting structure formation. Together, these limits leave little room for neutrinos to play more than a minor role. What neutrinos do provide is an important lesson. They show that weakly interacting, nearly invisible particles are real. They also help define what dark matter cannot be. Dark matter must be heavier and slower than neutrinos, allowing it to clump early and form stable structures. A calm way to think about this is to imagine trying to build sand dunes in a strong wind. Fine dust is blown away too easily. Heavier grains settle and form shapes. Neutrinos are like the dust. Dark matter must be more like the sand. By ruling out neutrinos as the main components, scientists refine the picture further. Dark matter must consist of particles that are relatively massive, slow-moving in the early universe, and stable over cosmic time. These constraints guide the next step in the story. In the next part, we'll explore how scientists classify dark matter by temperature, not literal heat, but motion, and why the idea of cold dark matter fits observation so well. When scientists describe dark matter as cold or hot, they are not talking about temperature in the everyday sense. They are describing how fast the particles move, especially in the early universe. This distinction turns out to be crucial for understanding how structure formed and why the universe looks the way it does today. Hot dark matter refers to particles that move very quickly, close to the speed of light when the universe is young. As we've seen, neutrinos fall into this category. Because they move so fast, hot dark matter particles tend to stream out of dense regions before gravity can pull them together. This makes it difficult for small structures to form. Cold dark matter, by contrast, consists of particles that move much more slowly early on. Their lower speeds allow gravity to gather them into small clumps, which can then grow into larger structures over time. This behaviour aligns closely with what we observe in the universe. There is also an intermediate category sometimes called warm dark matter, with particles that move at speeds between hot and cold. Warm dark matter can suppress very small-scale structures, while still allowing larger ones to form. Scientists study this possibility carefully, but current observations suggest that dark matter is mostly cold. The evidence for cold dark matter comes from several directions. The detailed distribution of galaxies, the presence of small satellite galaxies, and the fine structure of cosmic filaments all point toward matter that clumps efficiently on small scales. When simulations use cold dark matter, they reproduce these features well. When they use hot dark matter, the results look very different from reality. Another important clue comes from timing. Cold dark matter allows structures to begin forming earlier in cosmic history. This gives galaxies enough time to grow and evolve into the forms we see today. Hot dark matter delays structure formation too much, leading to a universe that is smoother and less complex than observed. The cold dark matter model also fits naturally with what we know about dark matter's weak interaction. Particles that interact weakly do not easily lose energy. They move according to gravity and remain spread out in large halos rather than collapsing into dense objects. This behaviour matches the observed properties of dark matter halos around galaxies. A calm, everyday comparison can help clarify the difference. Imagine pouring honey and water onto a flat surface. Honey moves slowly and gathers into thick pools. Water spreads quickly and evens out. Cold dark matter behaves more like the honey, forming concentrated regions that can grow. Hot dark matter behaves more like water, smoothing everything out. This distinction does not tell us exactly what dark matter particles are, but it strongly constrains their properties. They must be heavy enough to move slowly early on, they must be stable, and they must interact weakly with ordinary matter. By narrowing the possibilities this way, scientists can design better experiments and simulations. Cold dark matter becomes a working framework. Not a final answer, but a model that successfully explains a wide range of observations. As we continue, we'll explore how cold dark matter behaves in space today, focusing on the large, smooth halos it forms around galaxies and how those halos influence motion and structure. With the idea of cold, dark matter in place, scientists can describe how dark matter behaves across the universe today. While it does not form stars, planets, or dense objects, it does follow clear patterns shaped by gravity. These patterns are calm, stable, and extended over enormous distances. Dark matter tends to form large halos around galaxies. These halos are roughly spherical and extend far beyond the visible edges of galaxies. In many cases, the visible galaxy occupies only the inner portion of its dark matter halo. Stars orbit within this invisible structure, responding to its gravitational pull even though they cannot detect it directly. Within these halos, dark matter is relatively smooth. It does not collapse into a thin disk the way ordinary matter does. This difference comes from interaction. Ordinary matter collides, loses energy, and settles into flat rotating disks. Dark matter does not collide or radiate energy in the same way, so it remains more spread out. This smooth distribution is exactly what observations require. It explains why galaxy rotation curves remain flat at large distances. It explains why stars far from the galactic centre still feel strong gravity. And it explains why galaxies can remain stable over long periods of time. On larger scales, dark matter halos merge and connect. When galaxies come together, their halos interact first, guiding the motion of visible matter. Over time, this process builds up clusters and superclusters. Dark matter forms the backbone of these structures, linking them into the cosmic web. Another important behaviour of dark matter is its passivity. It does not react to light, heat, or pressure in the way ordinary matter does. Energetic events like supernovae can push gas around, but dark matter remains largely unaffected. This makes it a stable reference frame for structure. Simulations show that dark matter halos have characteristic shapes and density profiles. These profiles emerge naturally from gravitational interactions and are seen repeatedly across different simulations and observations. While details are still studied, the overall picture is consistent and robust. A gentle comparison can help visualize this. Imagine a large, transparent sponge soaked in water. The sponge provides structure and shape, while the water moves within it. Dark matter is like the sponge, invisible but defining the form. Ordinary matter is like the water, moving, cooling, and lighting up within that structure. It's also worth noting that dark matter does not dominate everywhere equally. Near the centres of galaxies, visible matter can be dense enough to compete gravitationally. Farther out, dark matter becomes dominant. This gradual transition helps explain the variety of galaxy behaviours we observe. Understanding how dark matter behaves in space allows scientists to test theories more precisely. Any proposed dark matter particle must lead to these large, smooth halos and stable structures. If it does not, it can be ruled out. As we move forward, we'll bring the discussion closer to home by looking at dark matter's presence in our own galaxy, the Milky Way, and what that means for us here on Earth. When we talk about dark matter on cosmic scales, it can feel very distant. But dark matter is not confined to faraway galaxies or ancient epochs. It is also present much closer to home, within and around our own galaxy, the Milky Way. Understanding its local presence helps connect abstract ideas to the environment we actually inhabit. The Milky Way is embedded in a vast halo of dark matter. This halo extends far beyond the visible disk of stars, gas and dust that we see in the night sky. While the bright spiral arms and central bulge define the galaxy's appearance, they represent only a small fraction of its total mass. Most of that mass lies in the surrounding dark matter halo. Astronomers infer the existence and shape of this halo by measuring how stars move at different distances from the galactic centre. Just as with other galaxies, stars in the outer regions of the Milky Way orbit faster than visible matter alone would allow. This motion requires additional gravitational pull, which the dark matter halo provides. The halo is not sharply defined. Its density is highest near the centre of the galaxy and gradually decreases with distance. Our solar system sits well within this halo, orbiting the galactic centre along with billions of other stars. Even though dark matter dominates the galaxy's mass overall, in our local neighbourhood its gravitational influence is subtle compared to that of nearby stars and gas. Still, its presence is constant. Dark matter contributes to the overall gravitational field that keeps the Milky Way intact. Without it, the galaxy's structure would be very different. Spiral arms would be less stable, the outer regions would not remain bound in the same way. Over long periods of time, the galaxy could lose much of its material. It's important to emphasise what this does and does not mean for everyday experience. Dark matter does not affect your weight. It does not change how objects fall on Earth. Its gravitational influence at human scales is extremely small. The effects we measure are collective, spread across vast distances and enormous amounts of mass. However, the fact that dark matter is present locally is important for experiments. Many direct detection efforts are designed with the Milky Way's dark matter halo in mind. As Earth moves through this halo, dark matter particles may pass through detectors on the planet. Knowing the expected density and motion of dark matter in our region helps scientists design sensitive experiments and interpret results. A calm way to think about this is to imagine living inside a very large, slow-moving current. The current is real, but its motion is gentle compared to the motion of nearby objects. You do not feel it directly, yet it shapes the larger flow around you. Dark matter is like that, a quiet background influence. Recognizing dark matter's presence in our own galaxy brings the discussion closer and more tangible. It reminds us that dark matter is not just a theoretical fix or a distant curiosity. It is part of the structure that makes our galaxy and our place within it stable over time. As we continue, we'll address a question that naturally follows from this idea. If dark matter is all around us, does it pass through us? And if so, what does that actually mean? Once we understand that dark matter fills the Milky Way's halo and that our solar system moves through it, a natural question arises. If dark matter is everywhere, does it pass through Earth? And if it does it pass through us? According to current understanding, the answer to both questions is yes. Dark matter particles, whatever they are, likely move through Earth and through our bodies constantly. This might sound unsettling at first, but it is important to approach it calmly and accurately. The key is interaction, or rather, the lack of it. Dark matter interacts extremely weakly with ordinary matter. That is why it does not pile up inside planets, stars, or people. It does not get trapped. It does not collide often enough to produce heat, radiation, or damage. From the perspective of dark matter, Earth is mostly empty space. From our perspective, dark matter passes by unnoticed. This situation is not unique in physics. Neutrinos, for example, pass through Earth in enormous numbers every second. Most of them travel straight through the planet without interacting with a single atom. Dark matter behaves in a similar way, though it is heavier and slower. Scientists estimate the local density of dark matter in our region of the galaxy. From this, they can calculate how many dark matter particles might pass through a given area over time. While the numbers can sound large, the interactions are so rare that their effect is essentially zero. There is no biological impact. There is no accumulated exposure. Life on Earth evolved in this environment without noticing. It is also important to clarify that dark matter does not surround us in a dense cloud. Its density, even within the Milky Way, is extremely low by everyday standards. The total mass is enormous only because it is spread across vast volumes of space. This helps explain why dark matter does not collect inside Earth. Ordinary matter loses energy through collisions and radiation, allowing it to settle into dense structures. Dark matter does not lose energy in this way. It passes through and continues on its path. A calm comparison can help. Imagine standing in a light rain where the drops pass around you without soaking you. The rain is present, but its interaction is minimal. Dark matter is even less interactive than that. It does not wet, push, or warm. It simply passes through. This understanding also frames why detecting dark matter directly is so difficult. If it passes through almost everything without effect, then any detector must be extremely sensitive and shielded from other signals. Even then, only a tiny fraction of particles would ever interact. So while the idea of dark matter passing through you may sound dramatic, the reality is quiet and uneventful. It has always been happening. It continues to happen. And it has no noticeable effect on daily life. As we move on, we'll look at how scientists try to detect these rare interactions anyway, using careful experiments, designed to catch the faintest possible signals of dark matter on Earth. Even though dark matter passes through Earth quietly, scientists have not given up on the idea of detecting it directly. Instead, they have designed experiments that listen patiently for the rare moments when a dark matter particle might interact with ordinary matter. These experiments are not dramatic, they are quiet, careful, and deeply controlled, built around the expectation that signals will be extremely rare. Most direct detection experiments are placed deep underground. This is not because dark matter prefers underground spaces, but because the surface of Earth is noisy. Cosmic rays, radiation from the atmosphere, and natural radioactivity can all produce signals that mimic the tiny effects scientists are looking for. By placing detectors beneath the layers of rock, much of this background noise is filtered out. The detectors themselves are often made of very pure materials such as liquid xenon, germanium crystals, or other carefully chosen substances. These materials are selected because they are stable and can produce a tiny measurable response if a particle interacts with one of their atoms. That response might be a small flash of light, a bit of heat, or a faint electrical signal. The idea is simple in principle. If a dark matter particle passes through the detector and happens to collide with an atom, it may transfer a tiny amount of energy. That energy is then recorded. The challenge is that such collisions are expected to be extremely rare, perhaps only a handful per year, even in large detectors. Because of this rarity, experiments must run for long periods of time. They must also be extremely well calibrated. Scientists spend years understanding every possible source of background signal, so that anything unusual can be identified with confidence. A single unexplained event is not enough. Patterns, statistics, and repetition matter. Another important aspect is that these experiments are designed with specific dark matter properties in mind. Different particle masses and interaction strengths would produce different kinds of signals. By tuning detectors to different sensitivities, scientists can explore a wide range of possibilities. So far, no direct detection experiment has produced a universally accepted signal of dark matter. This may sound disappointing, but in science, null results are informative. Each experiment that finds nothing helps narrow the range of what dark matter can be. It tells scientists which properties are unlikely and which remain possible. There's also a quiet optimism in this process. The universe has already told us that dark matter exists through gravity. The challenge now is matching that cosmic evidence with a laboratory signal. This takes time, patience, and precision. A calm way to think about these experiments is to imagine listening for a single, distant sound in a quiet forest. You do not expect it to be loud or frequent. You listen carefully, eliminate other noises, and wait. Even silence tells you something about where the sound is not coming from. As we continue, we'll look more closely at why detection is so difficult in the first place, and why even the most sensitive instruments struggle to catch dark matter in the act. To understand why dark matter has not yet been detected directly, it helps to pause and consider just how extreme the challenge is. The difficulty is not due to a lack of effort or imagination. It comes directly from the very properties dark matter must have in order to explain what we see in the universe. First, dark matter interacts extraordinarily weakly with ordinary matter. This is not an inconvenience layered on top of the problem, it is the core of the problem. If dark matter interacted more strongly, it would have shown up long ago in laboratories, in stars, or in everyday physics. Its invisibility is a consequence of its quiet nature. In most particle physics experiments, detection relies on frequent interactions. Particles collide, scatter, emit light, or leave tracks in detectors. Even neutrinos, which interact very weakly, can occasionally be detected because they are produced in enormous numbers and interact slightly more often than dark matter is expected to. Dark matter particles are fewer and quieter. Another challenge is energy. Dark matter particles move relatively slowly compared to particles produced in accelerators or cosmic rays. When they interact, they transfer very little energy. The signals scientists are looking for are extremely faint, far smaller than most background noise produced by natural radiation, cosmic particles, or even trace impurities in detector materials. This is why experiments must be shielded so carefully and constructed with such precision. Even tiny amounts of radioactivity in detector components can overwhelm a dark matter signal. Thermal vibrations, electronic noise, and environmental effects all have to be controlled and understood in detail. There is also uncertainty about dark matter's mass. If dark matter particles are heavy, they may interact rarely but produce larger energy deposits. If they are light, they may interact more often but produce signals too small to detect with current technology. Because scientists do not yet know which case is correct, experiments must explore a wide range of possibilities. Timing adds another layer of complexity. Dark matter interactions are expected to be random and infrequent. A detector might run for months or years without seeing a single event. This makes it difficult to distinguish a genuine signal from a statistical fluctuation or an unrecognized background source. Despite all this, the difficulty itself is meaningful. It tells us that dark matter truly is different from ordinary matter. Its reluctance to interact is not a flaw in theory. It is a defining feature supported by every observation we have. A calm comparison can help here. Imagine trying to detect a gentle breeze in a vast, noisy city. You would need to move far away from traffic, measure carefully, and wait patiently. Even then, the breeze might pass unnoticed most of the time. Dark matter detection is similar. The signal is subtle, and the environment must be quiet. Importantly, difficulty does not imply impossibility. It simply sets the pace. Science often advances by building instruments sensitive enough to detect effects that were once thought unreachable. The history of physics is full of such examples. As we move forward, we'll look beyond Earth-based detectors and explore how scientists search for dark matter, using space-based observations and cosmic signals, expanding the search to the universe itself. While Earth-based detectors wait patiently for rare interactions, another approach looks outward, using space itself as a laboratory. Space-based searches do not try to catch dark matter particles directly. Instead, they look for indirect signals, subtle effects or byproducts that might arise if dark matter behaves in certain ways. One idea is that dark matter particles could occasionally interact with each other. If they do, they might produce ordinary particles such as photons, electrons, or other detectable signals. These byproducts could travel through space and be observed by satellites and telescopes. This approach does not require dark matter to interact strongly with ordinary matter, only with itself. Scientists search for these signals in places where dark matter is thought to be especially dense. The centers of galaxies, including our own Milky Way, are prime targets. Dwarf galaxies, which are small but rich in dark matter and relatively quiet in other emissions, are also studied closely. These environments reduce confusion from other astrophysical sources. Space-based observatories are well suited for this task. They operate above Earth's atmosphere, avoiding interference from air and weather. They can observe high-energy particles and radiation across a wide range of wavelengths. By scanning the sky over long periods, they build detailed maps of cosmic emissions. So far, results from space-based searches have been intriguing but inconclusive. Some signals have been observed that could potentially be explained by dark matter interactions. However, alternative explanations involving known astrophysical processes often fit the data just as well. Pulsars, supernova remnants, and other energetic phenomena can mimic the expected signals. This ambiguity is not a failure. It reflects the complexity of the universe. Space is full of energetic events, and separating new physics from familiar processes requires careful analysis and restraint. Scientists do not rush to conclusions. Each potential signal is examined from multiple angles. tested against known models, and revisited as new data becomes available. Another indirect approach involves studying cosmic rays, high-energy particles that move through space. Some theories predict that dark matter interactions could alter the composition or distribution of these particles in subtle ways. Space-based detectors monitor cosmic rays with great precision, looking for anomalies that cannot be easily explained. What unites all these methods is patience. Space-based searches unfold over years and decades. Data accumulates slowly. Patterns emerge gradually. Each observation adds a small piece to a much larger puzzle. A calm way to think about this is to imagine listening for an echo in a vast canyon. You do not know exactly what the echo will sound like or when it will arrive. You listen, compare, and wait. Over time, the shape of the canyon becomes clearer. Space-based searches complement ground-based experiments. Together, they explore different aspects of dark matter's possible behaviour. Even when they do not find definitive answers, they help narrow the range of what dark matter can be. As we continue, we'll shift focus to another powerful tool in the search: particle accelerators, which attempt to recreate the conditions needed to produce dark matter under controlled circumstances. While some scientists wait for dark matter to reveal itself naturally, others take a more proactive approach. They try to create it. Particle accelerators, often called colliders, are designed to recreate extreme conditions by smashing particles together at very high energies. In doing so, they allow physicists to explore forms of matter that do not normally appear in everyday environments. The idea behind using colliders to search for dark matter is indirect but carefully reasoned. According to many theories, dark matter particles could be produced in high-energy collisions, similar to those that occurred in the early universe. If such particles are created in a collider, they would likely escape the detector without interacting, just as they do in space. At first, this might seem like a problem. How can you detect something that leaves no trace? The answer lies in balance. In a controlled experiment, scientists know exactly what particles go in and what energy they carry. After a collision, they measure all the outgoing particles they can detect. If some energy or momentum is missing, it suggests that something invisible carried it away. This method relies on careful accounting. Detectors surrounding the collision point are built to capture and measure a wide range of particles. By reconstructing the full event, physicists can infer whether an unseen particle might have been produced. These missing energy signatures are one of the key ways colliders search for dark matter. Colliders are especially useful because they allow scientists to test specific theoretical ideas. Different dark matter models predict different production rates, energy distributions, and associated particles. By comparing experimental data with these predictions, physicists can rule out or constrain large classes of theories. So far, collider experiments have not produced definitive evidence of dark matter, but like other searches, this absence is meaningful. Each null result helps narrow the range of possible properties dark matter can have. It tells scientists which theories are unlikely and which remain viable. Another important contribution of collider searches is their connection to known physics. If dark matter particles exist, they may be related to other particles or forces already studied. Colliders can probe these relationships, revealing whether proposed extensions to current theories make sense as a whole. It's also worth noting the scale difference between colliders and the cosmos. Colliders operate over microscopic distances and fleeting moments. Dark matter's most obvious effects occur over billions of years and across galaxies. The fact that these two scales can inform each other is one of the strengths of modern physics. A calm way to think about collider searches is to imagine recreating a rare, natural event in a laboratory. You may not know exactly what you are looking for, but you can control the conditions and watch for unexpected outcomes. Even when nothing new appears, you learn more about the boundaries of what is possible. Collider experiments also complement other approaches. Direct detection looks for dark matter passing through Earth. Space-based searches look for cosmic signals. Colliders look for dark matter being created, Together, these methods form a balanced strategy, each addressing a different aspect of the same question. As we move on, we'll consider what it means when experiments repeatedly find nothing new, and why in science the absence of evidence can still represent progress rather than failure. In science, it is natural to hope for clear discoveries, a signal that stands out, a result that settles a question. But much of scientific progress unfolds differently. Often, experiments run for years and find nothing unexpected at all. In the search for dark matter, this has been the case so far. Yet this absence is not empty. It carries information. Every experiment is designed with certain assumptions in mind. It looks for dark matter particles within a specific range of masses and interaction strengths. When an experiment detects nothing, it does not mean dark matter does not exist. It means that dark matter does not behave in the way that experiment was designed to detect. These null results gradually carve away possibilities. Entire classes of theories become less plausible. Regions of parameter space are ruled out. The picture becomes sharper, even if it is not complete. Over time, the remaining options become fewer and more focused. This process requires patience and restraint. It can be tempting to interpret silence as failure. But in careful science, silence often speaks clearly. It tells researchers where not to look and which ideas need to be revised or abandoned. There is also a deeper consistency here. The fact that dark matter has not been detected directly reinforces the idea that it interacts extremely weakly. If dark matter were easier to detect, it would have shown up by now in experiments, stars, or everyday phenomena. Its continued elusiveness is not a contradiction. It fits the observational picture. Null results also drive innovation. When one approach reaches its limits, scientists develop new methods, build more sensitive detectors, or explore alternative theories. Each generation of experiments builds on the lessons of the previous one. Another important aspect is humility. Dark matter is a reminder that nature does not owe us simple answers. The universe reveals itself at its own pace. Sometimes that pace is measured in decades, not years. A calm comparison can help here. Imagine searching for a specific shell on a vast beach. Each empty stretch you walk tells you where the shell is not. Over time, the search area narrows. Even if the shell is not yet found, the process is meaningful. In the context of dark matter, this steady narrowing has already taught us a great deal. We know dark matter is not ordinary matter. We know it is not fast-moving like neutrinos. We know it interacts very weakly. These constraints are powerful. As we transition into the next phase of our exploration, we'll widen the lens. Instead of focusing only on experiments and particles, we'll step back and look at what dark matter means in the broader context of the universe, its role in shaping patterns, scales, and long-term stability. After following the evidence, the experiments, and the unanswered questions, it can be helpful to step back and look at the broader picture. Dark matter is not just a missing piece in equations or a target for detectors. It is a foundational component of the universe's structure. Without it, the universe would look very different from the one we inhabit. Most of what gives the universe its shape does not shine. Galaxies do not float randomly through space. They gather into groups, clusters, then long filaments that stretch across hundreds of millions of light years. Between these filaments lie vast regions of relative emptiness. This large-scale pattern is not accidental. It reflects the distribution of mass, and most of that mass is dark matter. What is striking is how quietly this structure forms. There is no sudden construction, no dramatic assembly. Over billions of years, gravity guides matter into place. Dark matter settles first, outlining the framework. Ordinary matter follows, lighting up the structure with stars and galaxies. What we see is only the illuminated surface of something much larger. This perspective shifts how we think about visibility. Light becomes a tracer, not a ruler. It shows us where matter is condensed enough to ignite stars, but it does not show us where most of the mass resides. The true architecture of the universe is mostly invisible, yet deeply ordered. This idea can feel humbling, but it is also stabilizing. The universe is not fragile. Its structure is supported by something robust and persistent. Dark matter provides a steady gravitational background that allows galaxies to survive interactions, mergers, and long spans of time without dissolving. There is also a sense of continuity here. The same invisible framework that shaped the first galaxies continues to guide motion today. Stars orbit, clusters remain bound, filaments slowly evolve. Dark matter does not rush or fluctuate. It anchors change within a stable pattern. A calm way to reflect on this is to imagine a building supported by internal beams you never see. The visible walls and windows give it character, but the beams give it strength. Dark matter plays a similar role in the universe. It is not decorative, it is structural. Understanding this helps place our earlier questions in context. The search for dark matter particles is important, but even without knowing their exact identity, we already understand something profound. Most of the universe's mass operates silently, shaping everything without calling attention to itself. As we continue, we'll explore how this invisible structure repeats across different scales, from galaxies to the largest patterns in the cosmos, and what that repetition tells us about the underlying order of nature. One of the most reassuring aspects of dark matter is how consistently its influence appears across different scales. Whether we look at a single galaxy, a cluster of galaxies, or the largest structures in the universe, the same basic patterns repeat. Gravity behaves the same way. Dark matter distributes itself in similar forms. Structure grows through the same quiet processes. On the scale of individual galaxies, dark matter forms extended halos. These halos determine how stars move and how stable the galaxy remains over time. On larger scales, those halos interact and merge, creating groups and clusters. Zoom out even further, and those clusters connect along long filaments, outlining the cosmic web. This repetition is not coincidental. It reflects the fact that the same physical rules apply everywhere. Gravity does not change its behavior from one region to another. Dark matter does not adopt a new nature at different sizes. The universe builds complexity by repeating simple processes over vast distances and long periods of time. Simulations make this especially clear. When scientists model the universe starting from simple initial conditions and include dark matter, the same kinds of structures emerge at every scale. Small clumps form first. Those clumps merge into larger ones. Over time, an interconnected network appears. The details vary, but the overall pattern remains stable. Observations confirm this picture. Surveys of galaxies show filaments and voids that match what simulations predict. Clusters sit at the intersections of filaments. Smaller galaxies trace the same lines on a reduced scale. Dark matter provides the connective tissue that links all of these structures together. This consistency gives scientists confidence. It suggests that dark matter is not an ad hoc solution for one specific problem, but a unifying element that explains many observations at once. When a single idea accounts for behavior across such a wide range of conditions, it earns trust. A calm, everyday comparison might be waves on a beach. Small ripples near the shore and large swells farther out are governed by the same physics. The scale changes, but the pattern remains. Dark matter shapes the universe in a similar way, repeating its influence from the smallest galactic scales to the largest cosmic structures. There is also something quietly comforting about this regularity. The universe is not arbitrary. Its patterns are not random. They emerge from simple rules applied patiently over time. Dark matter is part of that patience, guiding structure without disruption. As we move forward, we'll turn our attention to time itself, how dark matter has influenced the universe's evolution over billions of years, and how slow, steady change can lead to the rich complexity we see today. When we think about the universe, it is easy to imagine dramatic moments, explosions, collisions, sudden beginnings. But most of the universe's structure was not built in moments like these. It was assembled slowly, over immense stretches of time. Dark matter plays a central role in this long, quiet process. From the earliest stages after the universe cooled enough for gravity to act freely, dark matter began to gather. Not quickly, not violently, but gradually. Tiny differences in density grew bit by bit. Regions that were only slightly heavier than their surroundings attracted more matter. Over millions of years, those small advantages accumulated. This slow assembly is one of dark matter's defining features. Because it interacts weakly and does not lose energy easily, it does not collapse suddenly. Instead, it forms stable, long-lived structures. These structures persist, growing through gentle accretion and occasional mergers rather than rapid collapse. Time matters here. The universe is very old, and dark matter takes full advantage of that. Given billions of years, even small gravitational effects become decisive. What begins as a nearly uniform distribution gradually becomes a network of filaments, halos, and clusters. The pace is unhurried, but the outcome is profound. Ordinary matter joins this process later. Once gas can cool and respond to gravity, it flows into the structures dark matter has already built. Stars form slowly. Galaxies grow through repeated cycles of formation and change. Nothing needs to rush. Gravity, acting patiently, is enough. This long timeline helps explain why the universe looks ordered rather than chaotic. Structures have had time to settle into stable configurations. Orbits become smooth. Clusters remain bound. The cosmic web persists without tearing itself apart. A calm way to think about this is to imagine sediment settling in a lake. Particles drift downward almost imperceptibly. Hours pass, then days. Over time, clear layers form. No single moment defines the process, yet the result is structured and stable. Dark matter assembles the universe in much the same way. This perspective also changes how we think about discovery. Dark matter is not something that flashes into view. It reveals itself through long-term patterns, the result of gravity acting steadily over cosmic time. Understanding it requires patience, both in observation and in thought. As we continue, we'll look at how this slow, steady influence contributes to stability in the universe, how dark matter helps prevent chaos and supports the enduring structures we observe today. As structures slowly assembled over time, another important role of dark matter became clear: stability. The universe is not just built from matter, it is held together by balance. Without sufficient gravitational support, structures would dissolve, disperse, or never fully form. Dark matter provides much of that support, quietly maintaining order on the larger scales. Galaxies are dynamic systems. Stars move, gas flows, and interactions occur. Left on their own, these motions could lead to instability. Stars might drift away. Spiral arms could unravel. Over billions of years, small disturbances could accumulate into major disruptions. Dark matter reduces this risk by deepening gravitational wells and smoothing motion. Within galaxies, dark matter halos help stabilize orbits. They provide a steady gravitational background that keeps stars moving in predictable paths. Even when galaxies interact or merge, their dark matter halos absorb and redistribute energy, allowing the visible components to reorganize without complete destruction. This is one reason galaxies can collide and still remain recognizable afterward. On larger scales, dark matter stabilizes galaxy clusters. The combined mass of dark matter in a cluster creates a gravitational environment strong enough to hold hundreds or thousands of galaxies together. Without that unseen mass, clusters would be transient gatherings, slowly drifting apart. Instead, they persist across cosmic time. Stability also appears in the large-scale structure of the universe. Filaments do not collapse into knots or disperse into emptiness. Voids remain relatively empty. The overall pattern evolves, but it does so smoothly. Dark matter provides the gravitational continuity that allows this gradual evolution rather than abrupt change. This does not mean the universe is static. Change still happens. Galaxies form, merge, and evolve. Stars are born and die. But these changes occur within a stable framework. Dark matter acts as a kind of gravitational memory, preserving large-scale structure while allowing local processes to unfold. A calm comparison can help here. Imagine a river flowing within a deep channel. The water moves, ripples form, and currents shift, but the channel keeps the river on course. Dark matter is like that channel, guiding motion without being seen. This stabilizing role also helps explain why the universe has had time to develop complexity. Life, planets, and long-lived stars require stability. While dark matter does not interact with these directly, it contributes indirectly by maintaining the environments in which they can exist. Recognizing dark matter as a stabilizing influence reframes it from being a mysterious extra to being a fundamental support. It does not compete with visible matter, it complements it, allowing structure to endure. As we approach the final stretch of our exploration, we'll gently reconnect this cosmic picture to human experience, not philosophically but observationally, by considering where we sit within this stable, dark matter-shaped universe. After tracing dark matter across galaxies, clusters, and cosmic time, it's natural to ask where we fit into this picture. Not in a symbolic or philosophical sense, but in a simple, observational one. We are part of a galaxy that exists because dark matter made it stable. Our position is ordinary, embedded within a structure shaped long before we appeared. The Milky Way did not form around us. We formed within it. Long before Earth existed, dark matter had already gathered into a halo, guiding gas into rotating patterns. Stars formed in waves. Heavy elements were created and recycled. Eventually, systems like our solar system emerged inside this stable environment. None of this required special conditions, only time and gravity acting within the framework dark matter provided. From our location, about halfway out from the galactic centre, we orbit along with billions of other stars. This orbit is smooth and predictable because the galaxy itself is stable. That stability depends not just on the stars we see, but on the invisible mass that surrounds and supports them. It's also worth noting how typical this situation is. Most stars in the universe exist within galaxies shaped by dark matter. Most galaxies sit within larger dark matter structures. There is nothing unusual about our placement. That ordinariness is part of what makes the science reliable. We are not observing dark matter from a privileged position. We are observing it from within its influence, just like everything else. This perspective can be grounding. The universe does not need us to function, and yet we function within it because its structure is steady. Dark matter does not respond to life or intention, but by shaping galaxies, it indirectly creates long-lived environments where complexity can arise. A calm way to think about this is to imagine living in a well-built city. You may not see the infrastructure, the foundations, the support beams, the underground systems, but your daily life depends on them. Dark matter is part of the universe's infrastructure. It does not notice us, but it makes our context possible. As we continue, we'll gently shift toward why the question of dark matter still matters today, not urgently, not dramatically, but as a steady thread of curiosity that continues to guide scientific exploration. At this point, it's clear that dark matter is not a temporary puzzle or a minor correction. It is woven into nearly every aspect of how the universe behaves, and yet, the question remains open. We know what dark matter does, where it is, and how much of it exists. What we do not yet know is what it is made of. That gap is why the question still matters. In science, unanswered questions are not signs of weakness. They are signs of direction. Dark matter points toward physics that may extend beyond what we currently understand. It suggests that the collection of particles and forces we know is incomplete. This does not mean it is wrong, only that it is part of a larger picture. The search for dark matter continues because it connects many areas of science. Astronomy, cosmology, and particle physics all meet at this question. Observations of galaxies inform laboratory experiments. Results from detectors shape new simulations of the universe. Progress in one area quietly influences the others. There is also practical value in continuing the search. Historically, fundamental discoveries about matter and forces have often led to new technologies, even if those applications were not imagined at the time. While dark matter research is not driven by immediate use, understanding the universe more deeply has repeatedly changed how humanity understands energy, materials, and space. Just as importantly, the question matters because it reminds science to stay humble. For centuries, light defined our view of the universe. Dark matter shows us that light reveals only part of reality. There may be other components, other behaviours, still unnoticed because we have not yet learned how to observe them. This does not mean the universe is unknowable. It means knowledge grows gradually. Dark matter was not discovered through a single insight, but through patient accumulation of evidence. The same will likely be true of its identity. A calm way to think about this is to imagine reading a long book where some pages are still sealed. You understand the story well enough to follow it, but certain details remain hidden. Turning those pages takes time and care. There is no need to rush. As we approach the final moments of this journey, we'll begin to slow the pace further. We'll return gently to where we started, not with new facts, but with a sense of continuity, and prepare the mind to rest within a universe that remains quietly structured, even where it is unseen. At the beginning, we noticed a simple tension between what we can see and how the universe behaves. That tension led us through galaxies, clusters, gravity, and time. Now we return to that same quiet idea with more clarity. The universe is not defined only by light. Much of what holds it together does not announce itself. It works steadily, without display. Dark matter is present in every step of that story. It does not rush. It does not flicker in and out of existence. It remains, shaping motion and structure in the background. Stars orbit because of it. Galaxies persist because of it. The large-scale patterns of the universe endure because something unseen provides continuity. What's important here is not mystery but reliability. Dark matter behaves consistently. It does the same thing in distant galaxies as it does in our own. It follows the same gravitational rules across time and space. That consistency is what allows science to study it, even without direct detection. There is a quiet reassurance in this. The universe is not held together by fragile coincidences. It is supported by stable components, some visible, some not. Light shows us where activity happens. Gravity tells us what is truly there. Returning to this idea can soften the mind. You do not need to visualize dark matter or imagine its particles. It is enough to understand that unseen structure is normal, not exceptional. In everyday life, many systems rely on things we do not notice directly. The universe is no different. As this thought settles, there is nothing left to solve in this moment. The question of dark matter remains open, but it does not need to be answered tonight. What matters is that the universe continues to function calmly, whether or not we fully understand every part of it. In the final moments, we'll let this understanding fade into rest, not as a conclusion, but as a continuation, a steady flow that does not demand attention. The universe does not pause when we sleep. Galaxies continue to turn. Gravity continues to guide motion. Dark matter remains where it has always been, shaping everything quietly. Nothing needs to change for rest to begin. You can let the idea settle now without holding on to details. There is no test, no resolution required. Understanding can be partial and still complete enough for calm. Science does not insist on certainty before rest. It allows questions to remain open. As your breathing slows, remember that stability does not come from visibility. Much of what keeps systems balanced operates quietly in the background. The universe is structured even where it is unseen. That structure does not depend on effort. It persists on its own. You are part of this steady motion, not separate from it, not required to observe it, simply carried along as everything else is by forces that do not hurry. Nothing is collapsing. Nothing is coming undone. The same gravity that holds galaxies together holds this moment steady as well. Everything flows. Sleep in that motion.